Hello, you're listening to Undisciplined podcast. Today we're talking to Professor Jun Otsuka from Kyoto University. Soon he has a book out, The Role of Mathematics in Evolutionary Theory, coming out with Cambridge University Press. We cover a lot of topics. I'm sure you will enjoy. Speaking to Professor Jun Otsuka from Kyoto University. Can you tell me about your position here?
Oh yeah, sure. Yeah, I'm an associate professor in the philosophy department of Kyoto University. So I've been here for 2 years. This is my third year. And before that, I worked in Kobe University, also as an associate professor for 2 years.
If you don't mind, can you tell me a bit about your educational background, undergraduate, postgraduate?
Yeah, sure. Yeah, I was born in Tokyo, so I came to Kyoto when so I was 19 years old. So I entered Kyoto University as a undergrad student, and so I major in philosophy. And then graduate philosophy department here, and then entered as a master student in Kyoto as well, and did masters and first 3 years of PhD work here. So that is coursework in Kyoto. I decided to study abroad, and I went to Indiana University to do a PhD in history and philosophy of science, because I was doing philosophy in Kyoto, so especially I worked in Spinoza, 19th century, 17th century philosopher. So, and at that time I changed a little bit of my mind, and so maybe I wanted to do more kind of scientific stuff or contemporary stuff. So I changed my field, and I changed my major to philosophy of biology. And to study the philosophy of biology, I went to in Indiana University, and that was, I guess, 2008. And there I did my PhD in the history of philosophy of science, and also I did my master's in statistics. And yeah, and I think it took like 5 years, and then did some postdoc at the UC Davis for 2 years, and then came back to Japan in Kobe.
Thank you. So I'm curious why you said before you were studying Spinoza, which is a kind of very classical philosopher, traditional philosopher. So you changed your mind, you wanted to do something more contemporary. Why? I can see with Spinoza the link to philosophy of science, but what was it that made you change your mind?
Yeah, so it's a long story, but to make it short, so I in my thesis, like BA thesis, I worked in the problem with teleology in Spinoza, the teleological explanation, that is the explanation that leads to a goal or end of behavior to explain the behavior itself. And there was a debate in the Spinoza literature at that time whether Spinoza, Spinoza is famous. Spinoza is known for kind of criticizing teleological explanation. So the kind of the official, the traditional interpretation of Spinoza is that Spinoza does not deal with teleological explanation at all. But some philosophers like Jonathan Bennett started claiming that, well, Spinoza implicitly uses teleological explanation. And so there's a problem at that time whether Spinoza allows teleological explanation in his work. So I was interested in that debate, and so I worked in teleological explanation, and that, of course, led me to work on what are teleological explanation, and what is it at all. And then I found that the teleological explanation is actually used in contemporary science, that is evolutionary biology. So at that time, the philosopher of biology discussed that actually the functional explanation, that is the explanation of biological traits like heart in terms of its function. That is, for example, the function of heart is to pump blood. This is a theoretical explanation, they said. So I found that, well, actually theoretical explanations are used in science and evolutionary theory. So then I have to study this explanation first to understand what is theoretical explanation. And that brought me to the general field of philosophy of biology. So I was interested in theoretical functional explanation in biology first, and then evolutionary theory in general.
This is interesting for me because this is, for me, giving a functional explanation is almost a kind of opposite to a teleological explanation of something. So if you say that even a biological function like a heartbeat has a teleological end, can you explain that to me? How does the functionalism go over to a teleology?
Yeah, sure. So the first thing to note is that function is not just what a thing does. For example, heart does many things. Of course, it pumps blood, but it does many other things as well. For example, it increases our weight, for example, to some extent. Of course, this is kind of very not interesting things that does, but at least it does something. And it, for example, make noise, heartbeat, and so on. But it's not a function, right? Nobody say that function of the heart is to make noise or to make heartbeat or anything like that. So there is a distinction between what it does and its function. And then the question is what makes some behavior function of that thing. And then the function is something that explains the origin of that thing itself. So when we say the function of heart is to pump blood, we say that because it pumps blood, there is heart. Well, heart is there in our body, right? So function somehow is a behavior that explains the origin or maybe maintenance of that trait in our body or in something. So yeah, that's how philosophers of biology define function. At least this is one way to define function. There are various other interpretation of function, but this is one way, teleological interpretation of function. And why is it teleological? Because what is teleology? Teleology is an explanation of something that resort to the behavior done by that something itself. So, for example, we say that what is a heart for? Like, what is a heart for? Well, it is for pumping blood. So this is, we cite its goal or kind of aim to explain the heart. So in a sense, a functional explanation in this interpretation is teleological. But the important things to note here is that teleology does not assume some kind of spooky mechanism. It doesn't assume that the future causally influences the past or something like that. So it's just a way of explanation. So it's a way of explaining things by resort to its outcome or its consequence and so on. So that's the reason that philosophers of biology at that time think that functional explanation is a teleological explanation.
So that also makes me wonder, if we speak about the function of something, I think perhaps in the case of a heart, that wouldn't be, the function is not so controversial, but perhaps in more complex situations, is the function of something, is that function intrinsic to the thing itself, or is that function projected or received by an external observer?
That's a very interesting question, actually. So, yeah, we assume, we usually think that function is intrinsic to an object. At least Aristotle thought that way. So according to the Aristotle's doctrine of four causes, that everything, well, there are four types of causes, and one is teleological cause and teleological explanation. And that explanation is based on the nature of the thing. So it is the nature of me of doing something. It's the nature of a rock of falling down, something like that. So in that interpretation, the goal or function of a thing is internal to the object itself. It's in its essence. But the modern thinker, like modern philosophers of biology, do not think in that way. So they do not think that function is an intrinsic feature of an organism or even a species, because it's completely determined by environmental pressure, the environment. Like if something has certain function, that is just in response to surrounding environment. And even if one has a function, that function does not necessarily contribute to that organism or that species in the current environment anymore. For example, some trait might be an adaptation to an earlier period, but that environment itself is not anymore, maybe. So for example, in human, this is especially the case because our environment has changed so much. A trait is function for something does not mean that it is still advantageous to do that thing. This is, I think, important because that function has some kind of normative implication. So if some trait, well, a function of some trait is to do something, say X, then people easily lead off the implication that it is natural for that thing to do X. And if it cannot do X, this is somehow imperfect or deficit or something. But this kind of normative claim is completely outside of the functional claim itself, because function is just a statement about history, and it doesn't say anything like it has to continue to do so. So just because that function as such, like X, does not mean that it still has to do this. Right? So yeah, this is very important, especially in today's like in sociological, in our social life. For example, I may have, so for example, eyes, well, because that a function of eyes are to receive the optical information, but some eyes do not do that. But that's just a factual claim, and it does not entail that there must be a kind of whatever. That means that there's a normative component. It is not legitimate to read off a normative claim that eyes must receive optical information or anything like that.
This leads me to thinking, so speaking of evolution more generally, so I think especially when we have conversations with friends in a bar or something, or in the media, the word evolution is used quite often, and I think it's definitely become a way for lay people to think about the world or their lives. But I feel like a lot of times people are not read in evolution, and certainly not up to date. Maybe they just have some vague idea of what evolution is about, Darwinian evolution. So what are, in general conversation or in the popular media, what are there any really popular misconceptions about evolution that are either outdated or were never true in the first place? One that I can think of is related to what you're speaking about, the normative aspect of functions. Is, I think, in the popular imagination, definitely evolution seems to be connected with the idea of progress. That's probably, at least from what I can see, one of the main misconceptions that people carry about evolution? Are there any others?
Yeah, you're absolutely right that the concept of progress is often tied to the concept of evolution, but they are completely two different things. Where progress has a certain kind of goal-directed process that has a specific goal, but the evolution does not have any specific goal. It is not directed to anything. So yeah, that is one thing. But the other thing, well, there are many things that I think that many misconceptions or kind of the difference in the terminology and so on, and also, especially in the States, the very notion of evolution is in doubt because of the creationism. So there are a lot of debate going on in the States. In Japan, the situation is, I think, not like the US. I think many people believe in evolution to some extent, I think. But I think that there are many misconceptions, I guess. And the difficult thing is that any misconception has some grain of truth. So it is not totally wrong. In many cases, they are kind of oversimplifications. And this such oversimplification is not harmless. So that's the problem, I guess. So specific example, well, I think there are many examples, for example, like concept of race. So that is that humans are distinguished into or classified into distinct races. And the races are different people belong to different races, have different dispositions and different maybe physical or mental properties and so on. So this concept of race has been criticized for many years in the biological community, and most notably by the evolutionary biologist Richard Winton. But it's die hard. I mean that it's still there, and so to define the concept of race biologically is not a simple thing at all. I do not say that it's impossible or it's illogical or anything like that. Well, it might be possible, but in many cases, it would be whatever it would be totally different from a common understanding of race and so on. So I think this notion of race is one example. And the other is concept of gene, which is, of course, very central to today's biology. But it is very hard to understand what is genes, and philosophers of biology have discussed for a long time what are they, what can they be, and so on. And also their ontological status, what they are is different, and also what they do is also different. So people often think that some of our properties are determined biologically, that is, they are described by our genes or DNA and so on, genome. But this distinction between nature and nurture is not so firm. So you cannot just say that this trait, for example, that my being, for example, a particular height is biologically determined, whereas I like particular food, it is not biologically determined or something like that. So, but this is not that simple at all. For example, and also people say that there's a gene for cancer, gene for IQ, and a gene for music talent, and so on. But the story is not that simple at all, because these abilities are determined at least not just by single gene, or not even combinations of genes, but combination of genetic factors and environmental factors as well. And they act non-additively. That is, there are strong interaction there. So it's not that simple to say that some of our abilities determined by nature and not nurture and so on.
I see. Okay. Thank you. So, speaking of genes, I think popular understandings of evolution brings me to the point of the name of Darwin is, of course, very famous, but if we speak about gene, that comes from Mendel, right? So from your work, I understand that there are three broad schools of thinking within evolutionary theory. One of them does stem from the tradition of Darwin and Mendel. Do you mind saying what the three branches are, or what their differences are very briefly?
Yeah, so philosophers of biology are interested in what our evolutionary theory is. And every scientific theory assumes certain, well, what do we say, ontology, or kind of building block of the world. For example, Newtonian physics assumes that the world is consist from a Newtonian particle that has a certain mass, and it is located in Euclidean space and has certain moments and so on. So this is a kind of basic building block of Newtonian physics. And of course, other physics, quantum mechanics, assume that different things populate the world, so they have different ontology. And the social science, of course, has a different ontology. Economics assume that, for example, the game theory assume that there are agents that had a specific goal function and so on. So every scientific theory has a certain ontology. And so I'm interested in what kind of ontology is assumed in evolutionary theory. And actually this is more or less studied by many philosophers of biology. And I think there are three ways of thinking about that biology, that ontology of evolutionary biology. The one is the so-called population thinking, which was proposed by the famous evolutionist Ernst Mayr. And the idea is that the basic entity of evolutionary theory is a notion of population. So the population, so we have to think of population as a base of evolution. The population evolves. The implication of that is that there is no fixed type or something. So human, or Homo sapiens, is a kind of population. And it's a population is just a collection of different individuals. And they do not necessarily share the essence, the common essence. It is very much difficult to extract all the essence of human beings. So Aristotle so that there is an essence for human beings, that is a rational animal and so on. But Mayr denied such essence to exist in biology, because that evolution is always changing population, so that there are always exceptions. The variation is ubiquitous, and only with variation evolution by natural selection happens. So variation is fundamental. The essence is just an artifact, and that put Mayr to put population as a basic entity of evolutionary biology. So that's one thing. The other, another way of thinking about evolutionary biology is, as you indicated, the notion of Mendel. So Mendel introduced genes, and that concept of gene was discovered in the beginning of 20th century. Yeah, the end of 19th century, beginning of 20th century. And that concept is that there is a fixed discrete entity called, or not fixed, a discrete entity called gene, and evolution is a change of that frequency of that discrete entity. So I and you may have the same gene, actually. So for example, in a very basic population genetics, you assume that, for example, two types of genes, large A and small a, and you track the change in frequency of large A and small a, so two different types. So in this concept, so we still have a variation. Not all individuals are same, but still individuals are kind of classified into distinct combinations of genes. For example, you might have large A, I might have small a, and my friend might have large a, but her friend may have large a. Then in that respect, you and her friend are the same. They have the same genotype type. So in this concept, population is kind of consisted of many types, many genotypes. So populations are kind of discrete. So we have discrete entity called type, and the evolution is change in that type. So this is not nonsense because it does not assume that everybody in the population has the same gene, but even still, it has a discrete entities that can be shared by different individuals. So this is another way of thinking about evolution, and I think this is the standard way of thinking about evolution, and that is one of the basic tenet of the so-called modern synthesis, which is the standard paradigm of the modern evolutionary biology. So yeah, these are two main ways of thinking about evolution. Yet the third way is to think a little bit beyond genes. So modern evolutionary biology think that genes are fundamental entities, but maybe there may be other kind of entities playing around. So for example, so some recent people discussed that, for example, epigenetics, the epigenome is also important. So gene get modified by phenotype and other activities. So, and these modified pattern for modification is also important. And also organisms or individual organisms create an environment in such a way that, for example, it is called niche construction. So they create niche. For example, beaver construct a dam, and that dam is also inherited. Well, for example, earthworms, they change the soil, and so then that environment is also created. That niche is also created and inherited to the next generation, and so on. So there may be things other than genes that are inherited, and that kind of make a evolving system beside genes. So that is somehow this view assume a somehow richer ontology. That is that their ontology contain not just genes, but maybe also epigenetic factor and niche and so on, or maybe developmental pathways and so on. So there is a debate between the classical traditional evolutionary biology, the so-called modern synthesis, and also there are some people who argue against that traditional view and argue that we need somehow extended evolutionary synthesis, that we need different framework and so on. I am a philosopher, so I'm not here to judge which is correct or not. But I think this is a scientific and empirical matter. But I'm interested in the debate, and so because this debate can often get intense, and often they talk past each other. So there is a misunderstanding between these two camps. So I'm interested in argumentative structure and their assumption and so on. So in some of my paper, I try to clarify the debate and their misunderstanding in terms of different ontologies. So they assume different things as basic entities, and that because some of their debate are so hard to understood by the other camp and so on. So this is, I think, what Kuhn has called the incommensurability between different paradigms. So I do not claim that they form two different paradigms, because I think our paradigms are more radical different and make a more radical difference. But there are somehow difference in conceptual framework, and that kind of difference sometimes makes scientific communication difficult. And as a philosopher of biology, I think one of our job is to organize a kind of to clarify the debate and point out what are the difference and what are the conceptual difference that makes the communication so hard. So that's what I'm trying to do.
Oh, thank you. That's very interesting. I want to go back to what you said about the niche construction. So it sounds to me, and please help me if I'm wrong, but it sounds to me that one of the differences there is that with niche construction, you're talking about evolution not just happening within, in the terminology I'm used to, is not just within the system itself, but that a feedback between the system and environment, and that if the system reproduces, that it inherits certain structures or functions from within the system, but that it also inherits its environment. That's very interesting to me.
Yeah, so the question of unity is always interesting. So, for example, we are a kind of system, right? We are a collection of bunch of different cells, and so we are kind of collection already. We think that we are individual by themselves, but actually these individuals are just a collection or group, and that group is so well coordinated, so we don't have to treat each cell as single individuals. But sometimes we have to treat this as individuals. For example, in the case of cancer is a case where the individual start to evolve by itself. So each cell increases incessantly, and that makes a lot of problem for the group itself. So we are a group actually, and also it is almost impossible for us to live alone. So we depend on social infrastructure. And so we create niche in that sense. Well, we create niche, and our niche is inherited from ancestors. So this is, in some sense, this is a whole system, whole social system that is kind of a unit, that makes a unit. Of course, that in human case, it is a little bit kind of controversial, because well, in some way, well, we can leave our society, and the society is still different. But in the case of bee and so on, so the colony is much more integrated. So in some way of looking at it, maybe a beehive can be its own entity. The idea is that individual is not just consist from biological entities, but it may also include some kind of environmental components that is obvious in beehive and so on, our social infrastructure. So we may say that the individual, not just group, but that group was evolving system may contain some kind of what we call environmental factor as well.
So where, if human beings and certain animals, or perhaps everything, is a collection of systems or different parts, where does the unity come from? Will we be going back to Aristotle to say that there's some kind of essence that makes it a unity, or is, like one of my first questions, is the unity projected from outside onto the collection?
Yeah.
Or is it a purely linguistic construction? Maybe that's too far, but...
Yeah, that's a very difficult and very interesting question, where the unity comes from. And that's a huge, this is a huge topic in biology, and also evolutionary biology, and also philosophy of evolutionary biology. We definitely do not want to go back to Aristotle and claim that there is an essence for species. That is a kind of dangerous mistake that the species has its own essence and the species evolve for its own shape and so on. This is, I think, no biologist or philosophy claim that way. No one holds that view. So, but even still, I think there's a kind of individuality here, so that we are not just collections of cells, but we are ourselves kind of individuals. And the individuals mean that there is some kind of unity. So where this unity comes from is a very difficult question. And that is a problem of what we call the problem of major transition. So at some point in the history, individual cells, or maybe bacteria living together started to form a certain individual. When and how, this is unsolved problem, and it is still happening, or maybe happening. For example, some group like beehive might be individual, then it might have some kind of unity, but what kind of unity is that? This is a difficult question, and what is necessary and sufficient condition for some group to become an individual or unified individual? This is an ongoing research problem, both empirically and also conceptually.
And it would perhaps, like I said in the beginning about function, saying that function is something that's projected by the observer. I suppose if we speak about unity like this, that answer wouldn't be enough. The unity is in the eye of the observer, and not in the thing itself.
Yeah, that's, I think, is a very difficult. I think we can think that problem in different layers. For example, in the deepest layer is how or whether our knowledge captures the world. So we think that there are, for example, fundamental particles and fields and so on. Are they real thing in the nature, or we adopt this terminology just to describe the nature? So why we think that why physicists talk about, for example, electron and other particles like charm and quarks and so on. So are they there, or they are a useful way of describing and explaining physical phenomena? The philosophers disagree about this between these two stances. One, the formal way of thinking, that is that quarks and electrons actually exist in the world, is called realist. And those who think that they are just kind of façon de parler, so they are just a way of describing the world, more anti-realist way of looking at science. So this is the deepest layer. So we use, for example, the concepts like individuals, genes, and so on, functions to describe and then explain evolution. But do they actually correspond to the nature of joint, that is a real objective feature? Well, some people might take anti-realist stance to it. But so this is kind of metaphysical and the fundamental layer. But without going that deep, I think there is still a problem about how our model fit to the world. So this is so functions and other concepts like maybe species, individuals, and so on. They are explanatory concepts. We use these concepts to explain the world. And to what extent they delineate the objective feature of the world, I think this is an interesting question. Well, I have to say I myself is kind of agnostic, and so well, maybe my stance is that they are part of models. So models are always fictions. So when we have, for example, models of any science like physics, like the planetary model of atoms and so on, this is not the real thing. This is a replica, or this is a kind of very simplified model. So we call it model. And any concept in biology appears in a kind of model. And model is not the real biological system itself. It is a simplified replica. And some aspect of it is really explanatory. So if model is explanatory, we have reason to think that its aspects somehow represent the world to some extent faithfully. So I think it's good enough. So I'm not sure if this really captures the real thing in the world or not. Maybe it's a façon de parler, but even still, I think that the model captures the world and the models are useful. Then I think this is I'm happy with that. Of course, there is a remaining philosophical problem, but that is, I think, a very kind of harder problem, and we, of course, that's interesting, but I think I will think about it later, maybe.
So one of the things I'm wondering is, as I said to you earlier, my own interest is in social systems theory. So it's taking a lot of biological metaphors like autopoiesis and also evolution to describe social systems, applying it to social communication between human beings. This has also been criticized by many, saying that it's misappropriating biological metaphors for non-biological phenomena. In your opinion, do you think it makes sense to speak of evolution in a social sense? I know that in the past, and perhaps what you said about racism earlier, it's definitely been abused, kind of social Darwinism thinking. But apart from those very obvious abuses, do you think there is any use to using these kind of biological metaphors such as evolution within a purely human social context?
Yeah, that's a very interesting question. So I'm not so familiar with the specific usage of evolutionary terminology in autopoiesis and so on. Well, I'm aware that they are used in these fields. I cannot say anything definite about it because I have to look at it. But in general, I'm kind of permissive about the use of translation or transportation of one terminology from one context to another context. This is how science works. I don't think it's possible for any scientific field to work without using any metaphors. So evolutionary biology uses a lot of metaphor itself. For example, it uses concept of information on the program. So it is said that DNA is a program that encodes phenotypic information and so on. These are, of course, borrowed from informatics and computer science and so on. And it is not directly used. I mean, the notion of program is not used as a program in computer science, and the information is not a Shannon information at all, and so on. So these are somehow kind of appropriated from different fields, and in some cases, they create a lot of misunderstanding. But even still, they serve for certain purposes, and they, I think, have some good about it. And also there's other metaphor like selective force, that every natural selection is a kind of force that moves the population. But again, this force, the concept of force is borrowed from mechanics, for example, Newtonian physics and so on. But of course, that force is not a Newtonian force at all. Yeah, biologists use a lot of metaphors like selfish genes and so on. It is impossible to do science without these metaphors. And I don't think there's any reason to rule out all these metaphors, because metaphor is a very very productive apparatus, and also it makes communication easier. But at the same time, metaphors are dangerous because it creates unnecessary confusions and misunderstandings and so on. So I guess that applies to whatever scientific field. So in many in social sciences, they use a concept borrowed from biology and evolutionary biology and maybe physics, informatics, and so on. But the use of metaphor itself is not bad by itself. But we have to be careful about its use. So, because as I said, the metaphor might create some kind of unnecessary confusion. And so there is no silver bullet to say that, wow, this use of metaphor is good and this is not good. So, but we have to be always careful, and we have to analyze the specific use of metaphor in each time. And I think this is that kind of conceptual work is one of the things that the philosophers needs to do.
To change direction slightly, we spoke about, you said, the two sibling disciplines of philosophy of science and technology studies. Can you elaborate to me what are the differences in focus between the two fields or the two disciplines? And you said you work specifically in the philosophy of science, where I'm slightly more familiar with STS. And I'm familiar with some of the writings in STS without having really thought of or read about the agenda or the meaning of the discipline itself, just kind of selected works within it. So could you outline the difference between those two?
Yeah, that's a very difficult, because that at least I'm not the best person to ask that question. I'm not so familiar with the history of philosophy of science, or let alone history of STS. But my understanding, so this is my understanding, is that philosophers of science, so we are interested in the kind of internal working of science, how science works internally, what is its logical structure, what are its assumptions, theoretical assumption, and what are its methodology, and how this methodology is justified from its theoretical actions and so on. So we, or maybe at least I am interested in this kind of internal working or logic of scientific practice. Whereas I think STS is more oriented toward an external aspect of science. So how scientific field, for example, is influenced by its social settings, and how a particular project is influenced, for example, the policy, contemporary policy, and economic situation, and technology, and so on. So I think STS sees science within a context. So how science respond to that context. So this kind of external approach, I guess, is, in my understanding, is what STS is trying to reveal, I guess.
Yeah, because I suppose so STS has a more of a sociological background or foundation.
Right. Well, I may be wrong, but my understanding is that the STS stems largely from Thomas Kuhn, and Thomas Kuhn introduced a historical perspective to philosophy of science. Bit large. So before Thomas Kuhn, logical positivist and Karl Popper, and they tried to characterize scientific investigation ahistorically. So science is a pursuit of truth. So when and who carried out that project is irrelevant. Of course, that might be an interest of a historian, but the history of philosophy is not the philosophy of science. The philosophy of science concerns just like an internal logic of scientific theory. But then Kuhn came and said that, well, understanding of history is important to understand what science is and how scientific practice, how science proceeds. And I think STS is much influenced by this Kuhnian emphasis on the history.
Okay, thank you. I think that makes it very, very clear for me. One thing when I was looking at your work that was surprising to me, I mean, interested in legal theory or legal philosophy, and I thought a philosophy of science, I could make a kind of jump in reading your work, but then, as I said to you, very quickly I started running into equation, and I was surprised to read that you say that we can use equations very accurately to predict evolutionary processes. Am I correct?
Well, not really. It is very difficult to predict evolutionary response. So in many cases, I don't think we have a very precise equations to predict evolutionary dynamics, at least in a real population.
What is the problem of prediction? Is it a problem of complexity?
Yes, problem of complexity. So so in typical evolutionary problems in evolutionary biology, so there are a lot of factors, potential factors that affect evolutionary change. And it is impossible to track all these factors, and it is very difficult to control all the factors. So it is, first of all, it is also it is difficult to determine the relevant factors, and even if you have specific factors, it is difficult to measure them. So there are a lot of errors, known and unknown. And these noises or errors make precise prediction almost impossible.
I see. So, but you have a book coming out from Cambridge University Press that will be out this year.
Yeah.
And the title of the book is The Role of Mathematics in Evolutionary Theory. Do you mind explaining what your book is about, and also what is the role of mathematics in evolutionary biology?
Yeah, sure. Yeah, so the relationship between mathematics and science is always a wonder to philosophers. So think about Kant. So he wrote the classic book, The Critics of Pure Reason. And one of the main goal or main motivation of that book is why and how you can use mathematics to describe the world. And he has in mind the success of Newtonian theory. So Newtonian theory was so successful, and it can predict planetary motion so well. But it is written in the language of mathematics. And this is a little bit curious, a little bit strange, because mathematics is something you create by your own head, in your head. Mathematics is usually understood as a purely a priori knowledge. So you don't have to check the world to see whether 1 + 1 = 2. You can figure out by yourself without looking at anything. So this is kind of surprise that you can use mathematics to describe actual course of physics, actual course of planet, and so on. So that was one motivation. He wrote his book, and his answer was that the Newtonian physics and the scientific knowledge is what he calls synthetic a priori. But that solution, a Kantian solution, has been challenged, of course, by later philosophers, subsequent philosophers, and so on. So this problem, the role of mathematics in science, is a traditional philosophical topic. Kant was interested in physics, but biology, especially evolutionary biology, is also rife as mathematics. So, for example, evolutionary biology has some very fundamental theorems or fundamental equations that describe evolutionary dynamics, like the Price equation or Fisher's fundamental theorem of natural selection, and so on. And these equations are sometimes called theorems. And the meaning is that theorem is something that can be derived from mathematics without empirical assumptions. So this is a priori. And then the question arises why these a priori theorems can describe evolutionary dynamics, which is an empirical phenomenon. So that is a question that haunted philosophers of biology since maybe the beginning of the field itself. So that is the topic of my book. So why mathematics can be useful ever in evolutionary biology. So that was a problem. And my answer in the book is that, okay, so many people call that mathematical equations a priori. But let's forget it for now and think what you need in order to predict evolutionary phenomena and so on. And then, evolutionary phenomena, the evolutionary theory is using inductive inferences. That is, you predict or explain the future evolutionary response based on past record. This is called induction. But the characteristic of induction is it is never 100% certain. So this is pointed out by philosopher David Hume in the 18th century. That is, the inductive inference is always variable, and nothing in your data guarantees that future behave in the same way. So you have to make some assumption, and that assumption Hume called the uniformity of nature. So that is, you have to assume that the nature behave in the same way in the present, the past, and the future, so that you can use the present data to explain or predict the future response or extrapolate the present data to future. So if evolutionary theory consists of inductive inference, you need a uniformity of nature. And what is that uniformity and how do you describe it? That uniformity in population genetics and evolution genetics is represented by a model, evolutionary model. And that model is described in turn by mathematics. So the mathematics in evolutionary biology or evolutionary genetics serves as a uniformity of nature. Okay, then how it can serve as a uniformity of nature? So where does this mathematics come from? What I discussed in the book is that there's a branch of mathematics or applied mathematics that is called causal graph theory. And the causal graph theory uses a mathematical apparatus like a probability distribution and a graph that describe the causal relationship to study the causal structure of a system. And if you use this theory, you can derive various evolutionary models that you use in inductive inference in evolution, that is, you use to predict evolutionary response. So if you use that particular field of math or mathematical theory, well, you can describe some kind of uniformity of nature in evolutionary biology, and that gives you a certain model that allows a prediction of evolutionary dynamics. So that is a role of mathematics in evolutionary biology. So the answer is, so what is a mathematics to begin with? Well, that mathematics is a specific field of a specific part of mathematics called the causal graph theory, which is specifically designed to represent the causal structure of the world. So in a sense, it is not purely a priori, because this is a representation of a causal structure. And as a representation of a causal structure, it serves as a uniformity of nature that allows prediction of evolutionary response. That's what I argue in my book.
Oh, that's very interesting.
Yeah, sure. Yeah, it's difficult to explain a book in the short sentences. Yeah.
Oh, but it's very interesting.
Oh yeah, your question was why? So why you need why you use mathematics?
Yeah, and then you said there poses a philosophical problem using mathematics in evolution. But I think you perhaps explained that already. You mean the point of mathematics being a priori knowledge. But then, yeah, what's interesting to me is that, as you said, causal graph theory, it's almost like a bridge between the a priori description of mathematics and then actual causal structure.
Yeah, I think it's a good way to put it. Yeah.
Yeah, that's very interesting to think about. I think we're getting towards the end. So I have two more questions that are unrelated to each other and also unrelated a little bit to what we've spoken before. So first one is, if we take evolution as a structure happening over time again and again and again, a repeating of this pattern that makes very unlikely situations likely. Out of a million possible selections, one gets made. It's a very unlikely yet productive force. If we take it, this unlikeliness seems to me quite incredible. If we think about entropy in the world, how is it possible that, I don't know if it's just evolution or what exactly is the role it plays, but that the fact that we have anything here, that you and I can be speaking to each other right now, seems incredibly unlikely. How is evolution kind of against the odds? Why do we have something instead of nothing?
Yeah, well, I understand this is a very interesting question, important question. I'm afraid if I have anything, I can say anything interesting about it. So yeah, I agree. I agree with I see the question here.
Or perhaps another way I can put it, if evolution is this kind of survival of the fittest, by far the majority of organisms or species do not survive. As I said, for every selection that gets made, an infinite amount are not made. So please correct me if I'm wrong, but it seems to me that evolution is working almost counterfactually or almost against the odds.
So what do you mean by counterfactually?
Okay, perhaps not counterfactually, but so unlikely. The nearly impossible is actually reality.
Yeah, I kind of understand the question, but at the same time, I'm still not so much clear about what the question really means. So, the problem I'm having is what is meant by unlikely. So, unlikely is used in many cases in different ways. One is that we just don't know, we just don't understand, we just can't believe, and that is, yeah, I think this is an appropriate response that, well, this is very unlikely, this is really surprising, the life on earth is very surprising, how can it happen? But I think this is a very natural way, and this is of course this is a wonder, but that wonder leads us to scientific and maybe non-scientific investigations, and I don't think that existence of that wonder itself is problematic or a puzzle. Of course there is a wonder, because we are limited beings, we don't know many things, or we know almost nothing, like Socrates. So we are always have wonders, and that wonder prompts us to investigation. So I think that is a healthy wonder, and there's no wonder that we have that kind of wonder. So we don't know anything about evolution and so on, right? We have just a hypothesis, and that hypothesis is plausible at some point, and compared to other hypotheses, it has a certain advantage. I think I would say that it has a lot of advantages. So we are betting our time and money on that hypothesis, and that's just it, I think, because that kind of wonder exists everywhere, right? So for example, why? So you say that why there's something instead of nothing? That is a wonder. I mean, why there's anything? I mean, for example, well, I don't know anything about cosmology, but it is said that our universe is so well fine-tuned in terms of parameters. So if some fundamental parameters, constants of physical, I don't know, constants are different, the universe was not possible. The universe as it is impossible. And also the formation of solar system and Earth is also very unlikely if you think about it. So we don't know why they happened, but that's why I think the physicists and astronomers keep trying to understand that why. And we can never ever get rid of all whys because we can always ask why after answer. So we have always a puzzle and wonder, but the existence of such wonder is not itself a puzzling because there's always a puzzle. And I think this is a very nice thing with this I think it's fantastic that we have always a puzzle. If we figure out everything, and if, for example, our existence, our life, or the existence of the universe itself is not a wonder, I think it's really boring.
So for my last question, I saw on your shelf you have a book on the environment. So this is also something that's part of my interest in international law. Of course, we have environmental law, and this is, if not the number one, at least one of the most pressing questions today is, of course, our climate situation, the climate crisis. What implications does that have for evolutionary theory specifically? Is it something that's talked about? Because I can imagine that there must be some connection, but I cannot imagine exactly what.
Yeah, sure. Yeah, I think there are two. In many ways, they are related. The one is on the empirical ground. Changing in climate means a change in the environment, and so it impacts biological life on the Earth. And so I'm not so much familiar with empirical studies on that change in the environment, but they hear a lot of studies working on the evolutionary response induced by or are likely to be induced by climate change. Yeah, so that's of course has a biological impact. Climate change has the Earth has had several climate change, of course, from the beginning, and at that time, in each time, the life on the Earth had to respond to the change in the climate, and that shaped the current tree of life. So it is, of course, that the current change in climate affect evolutionary response. And well, of course, we don't know much about that, but we can certainly think that it is changing biotic environment. So that's one thing on the empirical ground. And a more philosophical ground is that so climate science itself is a very interesting topic, pose a philosophical question, because I said earlier that evolutionary biology is so complex, so it is very much difficult to make a certain prediction. And climate is also a very complex phenomenon. So it is very difficult to make a prediction. But you have to make prediction to say something about climate change. So there is a huge epistemological problem about climate studies. So some philosophers, actually including my supervisor, Elizabeth Lloyd as well. So she is now working on the philosophy of climate science. So philosophers of science recently, more and more philosophers turned on this problem of climate science and try to understand what is the empirical or epistemological, what kind of epistemological justification is available in climate science, and what makes its conclusion secure or vulnerable, and what is its characteristic, how is it different from other scientific fields or not, so how the model is used in climate science, and these are all interesting topics actually.
So you're in a problem if you move to America because neither evolution nor climate crisis exists there. So that would be one solution for all of us to move to America. But
well, I don't know whether it exists. It might not exist subjectively, but it might exist objectively.
But yeah, thank you very much. I think that's thank you very much.
Sure. Yeah, my pleasure.